Okay, more of Chapter 3 review. This is number 27. Y equals z times z inverse cotangent of z minus the square root of 1 minus z squared. So we got two basic terms here, so I highlighted these two terms by separating that. And then again, we have a product rule in the first term, and then we just have a straight out derivative with the chain rule in the second term. So if we look at this, the first is z times the derivative. The inverse derivative of the inverse cotangent of z would be negative 1 over the square root of 1 minus z squared. Okay, now remember that's just z, so that goes in there. There's no chain rule involved. Okay, plus the second, which is the inverse cosine of z. Okay, again, that's z inverse cosine of z. So again, that's going to be first times the derivative of the second, which is negative 1 all over the square root of 1 minus z squared, plus the second, that's our inverse cosine of z, times the derivative of z, which is just 1. Okay? And then this is negative, and then remember we could just use our basic rule. The derivative of the square root of x is just 1 over 2 times the square root of x, except we got the chain rule. So this is going to be 1 over 2 times the square root of this 1 minus z squared times the derivative of this, which is going to be the derivative of 1 is 0, and that's going to be negative 2z. And then what we can do is we could just put negative z all over the square root of 1 minus z squared plus the inverse cosine of z, and then a negative times a negative is a positive, the 2's cancel, so I got z over the square root of 1 minus z squared, and then these are identical terms but with opposite signs, so they add up to be 0, and this is what's left. Just the inverse cosine of z. Okay, and then number 29. I could have used a little more paper on this one. You'll see why in just a moment. So this is number 29. Let's get this down a little bit here. Let's get this up a little bit there so we can see all this stuff. And you may have to zoom in on this a little bit because I got a little small here in my writing, so hopefully you'll be able to follow all of this. This was a toughie. Okay, so we have our function is y equals the inverse cosecant of the secant of x, and the interval is 0 to 2 pi inclusive. Well, we're going to take the inverse cosecant of something, so we're going to have to use the chain rule and multiply by the derivative of that something. So if u is a secant of x, du dx is secant tangent of x. So this is what we've got. There's a lot of things going on in this problem. It's kind of cool. Okay. So the derivative of the inverse secant of something would be negative 1 over the absolute value of that something times the square root of that something squared minus 1. Okay. Times the derivative of that something, and the derivative of that something was secant x tangent x. So again, this is my u. So it's going to be negative 1 over the absolute value of u times the square root of u squared minus 1 times du dx. So there we go. Okay, now we have a lot of kind of creative algebra and trig to kind of figure this out. Now, I got secant tangent, I got the absolute value of the secant down here, and then I got the square root of the secant squared of x minus 1, and this kind of looks familiar, so I go back over here and I use my Pythagorean identity that I know. Sine squared plus cosine squared equals 1, divided by the cosine squared, I get secant squared tangent squared plus 1, that's my relationship. And then if I subtract 1 from both sides, it looks like the tangent squared equals the secant squared minus 1. So instead of writing this, I'm going to write the tangent squared. Okay, so I got negative secant tangent all over absolute value secant times that. Now remember, if you see the square root of x squared, the square root of x squared is just another way of writing the absolute value of x. I don't have room to write it over here, but the square root of x squared is the same thing as the absolute value of x. So the square root of the tangent squared is just the same thing as the absolute value of the tangent, so I can kind of put that underneath here like this. So on the top I've got negative secant tangent, and I got the absolute value of secant times the absolute value of the tangent, and you could put those both under the absolute value, under the same absolute value. because it kind of works like radicals. Okay, now here we go. I don't really know too much how to simplify this right now, so what I'm going to do is I try to put everything in terms of sine and cosine. So this is 1 over the cosine. This is the sine over the cosine, and we're multiplying these. And this is 1 over the cosine, and this is the sine over the cosine. Now what happens when I multiply these, I get the cosine times the cosine is the cosine squared, and the same thing inside this. I can put these both under the same absolute value. But the cosine times the cosine is the cosine squared. And what do we know about the cosine squared? Well, it's always positive. We're squaring something, it's always got to be positive. So I've got the sine over the cosine squared on top, but on the bottom I've got the absolute value of sine over the cosine squared on the bottom. So now I can multiply the top and the bottom by the cosine squared of x, and these will cancel, so I just end up with negative the sine of x over the absolute value of the sine of x. So that's one way I can get this cosine out of the absolute value, by realizing that if it's squared, the square root of something squared is just the absolute value of that something. So then I can multiply the top and the bottom, like I said, by the cosine, or 1 over the cosine, and it will cancel out. So we've got this. Now we've got an absolute value. Let's take a look at this sine graph. And the sine is positive from 0 to pi, and it's negative from pi to pi over 2. The sine is. So by my definition of my absolute value, I've got negative, I've got the sine of x, and then from 0 to pi, this will be positive, so I just leave it. I leave the bottom, the absolute value, the same, because this is going to be positive above the graph. Oops, let me show you the graph. I got it down. It's easier when you see the graph. You can visualize it. But when you see the graph, this is my sine curve, and from 0 to pi, from this interval here, the sine will be positive. This is going to be positive, but this will be positive. So the absolute value of a positive is just the positive value. So that's what I have. And then that's just 1. So I got negative 1. Now, from pi to 2 over pi, I'm sorry, from pi to 2 pi, this interval here from pi to 2 pi, notice how the sine curve is negative. Okay? So since that's the case, and we're going around the pi value, in other words, we would have 0 in the denominator if it was 0. So we're going around that. Okay, and we can simplify this. Then what happens is this is negative, so the absolute value of a negative something is negative that to make it positive, so this becomes negative sine of x, because it's negative down here, so it's negative sine of x. And a negative times a negative is a positive, so it ends up just being positive 1. And that's on this interval pi to 2 pi. So they kind of cancel out. So I think that's why we get away with what's happening here at the intervals, at the endpoints, excuse me. Now we have to say that x cannot be pi over 2 or 3 pi over 2 because the cosine here is in the denominator in these forms, and we can't have 0 in the denominator. So we can't have pi over 2 or 3 pi over 2. Okay? So again, this is going to be the same value because it's positive, and it's going to be the opposite value because it's negative, and that's going to give me actually a negative 1, and then it's going to be a negative over negative is a positive 1 for this range. So that's a little tricky, a little complicated. I hope that makes sense. And again, we have to put these stipulations in for 1 over the cosine, because these are the values when the cosine is 0, and we're simplifying, assuming that the cosine of x is not 0. Okay, I hope that helps. That was a tough one.